basically what I'm going to do for the next 20 minutes, half an hour or so, is run through options which we have looked at Historic Environment Scotland to make older buildings more energy efficient. Now, we'll take maybe 20 minutes, half an hour or so for this. There is a version of this talk that lasts for 4 days. So we are condensing, no pun intended, a lot of information into a very short space of time. So I'll cover as much as I can, and hopefully it will get us all thinking about methods and materials that we can use to make our older, traditionally constructed buildings in Scotland more thermally efficient. Now, wait a minute. Why am I not moving on? There we go. Right. Now, before we go on to think about internal wall insulation or roof space insulation or improving windows or anything like that, we have to take a step back and we have to think about how our buildings work. How do they work in terms of moisture movement in particular? In the 4-day version of the talk, I spend about 1.5 to 2 days on air and moisture movement. So if you think, wow, that guy's going on a bit, you're very much the lucky ones, because this could go on for a long time. I have just a few slides about this. Essentially, what I want us to think about is the amount of moisture that our traditional buildings have to deal with. So on the right-hand side of the picture here, the wee diagram, you've got the outside of a mass masonry wall, and it has to deal with a lot of moisture because it rains, and climate change means it will rain more in Scotland. So the outside of our mass masonry wall is getting wet. When it rains, the sun comes out, the moisture leaves the wall. What is much less apparent, though, is the amount of moisture that wall has to deal with from the inside of our buildings, because we produce a lot of moisture internally in our homes. We have showers and baths, we dry clothes, we boil potatoes, we breathe, our pets breathe. All of these things produce moisture internally. And that too can enter into the fabric of a traditional mass masonry wall and then dissipate back out again. So we have, with our traditional built environment, a situation whereby moisture can enter into the fabric of the building. It can enter into stone. It can enter into lime mortar and lime plaster and lime render. It can enter into roof timbers, and it can enter into floor timbers. So that moisture will go into our traditional buildings and the fabric that has created them. And we must make sure that we can let that moisture back out again. And we mustn't do things that compromise the dynamic whereby moisture moves around. As I say, that's a simplified version. The other side of moisture movement is air movement, and the movement of air in and around and back out of our traditionally constructed buildings is absolutely integral to how they work. This diagram is taken from a 19th century building manual. And if you spend your spare time reading 19th century building manuals, like I do, then you will find that they are absolutely stuffed full of ventilation diagrams. Quite a simple dynamic with this building. We have the fresh air chamber down at the bottom. So you can perhaps make that out. I don't know if I do this, maybe I can point to it. I can, look at that. So we've got the fresh air chamber down here. And these wee arrows, they show how air moves around the building until it comes to the foul air chamber up in the roof space. And it then percolates out through vents and through gaps between the slates. And that is essentially, I won't be able to get rid of this wee dot now, will I? I'll just put it down here. That essentially is how air moves around a traditional building in a domestic setting. Those twin actions of moisture in and moisture out of the building fabric and air coming in and circulating and leaving the building, that's what keeps our traditional buildings ventilated and free from rot and decay and mold and other things that we don't want to happen. If we neglect the movement of moisture, if we neglect the movement of air around our traditional buildings, we can in effect make them uninhabitable. Now, this building was one that we did some work on, and it had been retrofitted with internal insulation. So the walls and the roof space had been retrofitted. And this is what happened within about 6 months of that retrofitting work taking place. This wasn't even the worst bit of the house. So that's what had gone wrong here. And if I get my wee laser pointer back, the tracks which you can see here in the mold, those were made by slugs. So think on that. The building has gone so wet and so moldy that the people had to move out. So the tenants of this building had to move out, but slugs moved in. So that's what happens if you neglect air and moisture movement. Now, I will allow for the fact that this was quite an extreme example, because not only had the wrong choice of insulation been used, but every conceivable pathway for air to go in or out of the building had been sealed up. Subfloor vents sealed up, trickle vents sealed up, extract ventilation turned off. So it was a bit of a perfect storm, this building, but it very much illustrates what can go wrong. So we have to think about our traditional buildings in a different way when we're seeking to make them more energy efficient. We can't just treat an old building in the same way that we would treat a new building, because they are fundamentally different. An old building generally will have, say, 600 mil thick walls, mostly in Scotland built of stone with lime mortar as its bedding material. We have a lot of timber as well. Timber in the floor, timber in the roof, timber windows. All of those materials allow moisture to move around and need air to keep them dry and ventilated. So we have to treat traditional buildings differently. That doesn't mean, though, that we have to leave them inefficient thermally. There's lots that we can do to make traditional buildings more energy efficient, but we just have to bear those points in mind. So I'm now going to really quickly go through a whole bunch of different improvement options for different parts of the building fabric, always with air and moisture movement in mind. Now, we'll think firstly about windows, and in the next 15 minutes or so, I will talk an awful lot about U values. To put it simply, a U value is a way of expressing how much heat passes from inside a building through that building element to the outside. And the higher the U value, the more heat is lost through that building element. If we were doing this face to face, I could judge whether I had explained that successfully by the number of blank, confused looks. But I'll just have to assume that's reasonably clear. An unimproved single glazed window has a U value of around 5.5 or thereabouts. And that means that quite a lot of heat passes through that single pane of glass from the inside of a house to the outside. But there are things that we can do to make that window more thermally efficient. And crucially, we can do that without resorting to taking out a window, which may last for 100, 150 years in some cases, throwing it in a skip and putting in a UPVC window that might last 30 years if it's doing well. So there's a lot that we can do to improve sash and case timber windows. If you have shutters in your house, use them. They make a significant difference to the thermal performance of a window. Likewise, curtains and blinds and other infrastructure such as that, but shutters in particular give a very good level of thermal improvement. We can also think about draft proofing our single glazed windows. And this is normally the point, again, if I'm doing it face to face, where somebody says, well, what's the difference between drafts and ventilation? And the first time I got asked that, it threw me off a little bit. But now I've done hundreds of these kinds of talks, I've got a stock answer. And that is that ventilation is designed to be there, a draft isn't. And traditional buildings were not designed to be ventilated by rattly windows that don't quite fit in their frame anymore. So we're quite comfortable with draft proofing from that perspective. It doesn't improve the U value of the window, so the same amount of heat is still lost through that single pane of glass, but it will certainly reduce heat loss around the frame. For a more substantial improvement, secondary glazing is something that we've used in a number of the buildings which we have worked on. The level of thermal improvement varies a bit depending on what type you use, but in the case that you can see in the picture there, we got the U value down to 1.7, which is a pretty reasonable improvement. And this is a summary of all the different interventions which we have made to windows and how they have improved the thermal performance of single glazed windows. I'll refer right at the end to further reading and stuff like that, but this table is from one of our technical papers. So if you want to see the data which lies behind this, then it's available on the website. So you'll see all sorts of different levels of improvement. Right at the top, if you have space, and not everybody has space in their window reveals, to have secondary glazing and close your shutters, you can get the U value of the window down to 1.1, which is a 75% improvement in the thermal performance of the window. So we shall continue to plough on through the different parts of a traditional building. That was windows. We'll now turn to walls. And first of all, we'll look at internal insulation. So insulating inside a building. We've looked at three broad approaches to internally insulating mass masonry walls. We've looked at where there's a wall lining, so lath and plaster would be the traditional type of wall lining. We've looked at putting an insulating material in behind that, so in the space between the lath and plaster and the masonry. We've also looked at materials which are applied hard against a masonry wall. And lastly, we've looked at materials where you build a frame off the wall and put in an insulating material that way. When we first started our research into this 12 years ago, I had hoped that by now I might have the answer, the one material and the one method that would apply to everybody, and it would make my life a lot easier. It's not worked out that way. There are undoubtedly pros and cons for each method and material. And it's really up to you all as building owners and managers and people who care for traditional structures to make up your own minds about what is most appropriate for the building which you're dealing with. So we've looked at putting in something behind a wall lining. So lath and plaster wall lining, or it could be later plasterboard. And we've looked at this stuff, open cell foam. We put that in behind a lath and plaster wall lining in a building in Perth, and we monitored it to see how it worked. I don't know where my U value is gone. There should be a U value just about there, and it should say 0.5. It seems to have disappeared. Essentially, a mass masonry wall in Scotland will have a starting U value of about 1.2. Now that varies a bit, but if you have that in your mind as a starting point, this material put in behind wall linings improved that down to 0.5, which we're pretty pleased about. Some caveats with this: if you're putting anything into that space between a wall lining and the masonry, you will be reducing ventilation into the roof space. So you may have to think about putting in some slate vents up in the roof to compensate for that. So that's certainly something to consider. And depending on the material, you may have to make sure you're not just filling up the void beneath the floorboards. Not that we would do that. We're too smart for that. We understand buildings, and we would never just stand there putting stuff in thinking, where's it all going? That was definitely not us. That was somebody else. So there are some things to bear in mind with this, but thermally, it worked pretty well. And in terms of moisture, we monitored how the wall performed with moisture going in and out, and it continued to work well with this material in place. We've also looked at materials applied on the hard, is the traditional term for it, so stuck straight onto the masonry. You can see here some calcium silicate board being applied on the hard, so it's stuck on with the adhesive mortar, which is the kind of grey brown stuff you can see in the wall. And we got around about a 50% improvement in the U value of the wall with that, which was okay. It's not spectacular, but it's not too bad. Where calcium silicate board is really good is in buffering humidity. It will take in quite a lot of moisture and then release it again as conditions allow it to dry out. So it's quite good at buffering big spikes in humidity internally. We've also looked at aerogel blanket applied on the hard, and this is a stairwell in Rothsay, one of our other case study projects. U-value improvement 1.3 down to 0.6, which is really good in the context of there only being 10 mil of thickness of insulation. So aerogel blanket is only 10 mil thick. It's a very interesting material. It's interesting to work with. It comes in the form of, well, it's called a blanket, but it's sort of the consistency of a carpet tile, I guess is the best way to describe it. It allows moisture to move, so it gets a tick for that. Where it's very good is in situations like this, where you maybe don't have much space, or you have, say, a curved substrate, as we had here. There, that flexibility in the material is good at applying it onto a curved surface. The caveat for aerogel blanket is largely the cost. It was costing us £70 a square metre. So you guys can do the maths on your own walls, but it is an expensive way to insulate a building. And probably it's mostly applicable in situations like this, which you don't have much space to work with. In terms of materials where we've built a frame out from the wall, this is wood fibre board, which you can see held in place with a frame. There's about a 50 mil gap between the wood fibre board and the masonry behind. The U-value improvement that we got with this material was very good indeed. So we got the U-value of that down to 0.19. That building's in South Uist, where we did a sort of whole house refurbishment. And it was very successful indeed. That wood fibre board, like I say, very good in terms of thermal performance, good in terms of moisture movement. So that was quite a successful trial. Now, that was all internal, and there's probably another 8 to 10 materials that we've tried. If you want to know more, I'll refer to further reading at the end. Moving away from internal wall insulation to external, we've not done as much work on external wall insulation for a reason that I'll come on to in a minute. But we have used this material, wood fibre board, but used externally. So you can see it's stuck onto the wall. This is in Glasgow. With these wee white fixings that you can see here, those are called thermally decoupled expansion fasteners. It just rolls off the tongue after you've said it many times. The board is applied straight onto the wall, and it's then finished with this vapor permeable render that you can see here. Decent improvement in performance, 1.3 down to 0.4 in terms of thermal improvement. Permeable to moisture, so quite happy from that perspective. But the caveat with any external wall insulation is detailing in a retrofit situation, so detailing external wall insulation to a building which is maybe 100, 150 years old, can be very challenging. Now I'll get my wee laser pointer back. This building here, which is up in Shetland, if we just consider it for a minute, let's imagine we're going to put on 100 mil of external wall insulation. Well, I would have to extend the roof out because it doesn't project far enough to cover my insulation. I'd have to take the downpipe off and then reinstate it, and I'd have to alter the detailing here where the pipe meets the gutter. The windowsills don't project far enough, so I would have to extend the windowsills. I'd also have to detail the insulation around this porch whilst trying to avoid what's termed thermal bridging, or cold spots, for want of a better phrase, which would be incredibly challenging, especially given the proximity of this ridge to this window ledge. There's also a drip detail up here, which I may bridge if I put on my EWI. And that's before I go round the back and I discover there's a little extension, and that causes me even more problems. So the detailing issues in this, this is a pretty simple building in terms of its geometry. The detailing issues are substantial. This building here, well, we've got a parapet gutter, we've got downpipes, we've got drip details, we've got all sorts of odd detailing that would be very challenging indeed. And this building here in Glasgow, even leaving aside the aesthetics, to install external wall insulation just to this curved section here would be very hard indeed. So detailing is very hard to get right with EWI in a traditional building. That's not to say it can't ever be done, but what I would say is if any of you as building owners are considering it, make sure that all of that detailing is taken into account and it's fully costed for, because it will be expensive to do work to window ledges, downpipes, gutters, drip details, all of that sort of thing. Now, get rid of this. So there we go. That was walls. A quick run through walls. We'll now crash through lofts and roof spaces. Essentially, if you're insulating between the rafters in a traditional building, you can do it. We've got sheep's wool here. This is Edinburgh Castle, just to prove that we insulate our own buildings as well as other people's. So we've got sheep's wool in between the ceiling joists here. We got the U-value improvement of that ceiling from 1.5 down to 0.3. We did, in a different building, use wood fibre board between the joists. We got that down to 0.2 in that case, but that was harder. It was harder to cut the wood fibre board to fit snugly into that space. More challenging is if you have a room in the roof, and we've done a few of these now. This one here on the left, this one's in South Uist again. And what we did here was we removed parts of the ceiling lining. So the blue section is the pitch and the white section is the little half wall. We took parts of the ceiling lining off. We slid wood fibre board down into that space, leaving a gap between the insulation and the sarking board of around 30 to 40 mil. That was to allow ventilation to continue to flow between the insulation and the slates to keep the roof timbers ventilated. So you can improve rooms in the roof if you are careful about it. The picture on the right is a very similar situation, but there was no ceiling lining. So we installed our wood fibre board insulation and we finished it with plasterboard. Now, caveats. There's always caveats. With roof spaces, it is absolutely vital that we consider air and moisture movement, just as it is with any other part of a building. The images that you can see here are a building which was insulated just below here. So the insulation went in just a little bit below where my pointer is just now. Beneath the slates, there was bituminous roofing felt, so black roofing felt between the sarking board and the slates, and that was preventing warm, moist air from escaping. Now, that situation had existed just about happily enough for 30 years or so, until the insulation went in. So when the roof was insulated down here, it made the sarking board colder. And when you make part of a building colder, the risk of condensation forming on that part of the building goes up. When you get condensation on a piece of building fabric, mold won't be far behind. And that's what we can see here, mold forming on the now wet timbers. And as we all know, when timber gets wet, it will start to decay fairly quickly. So we must be aware of what we're doing in terms of moisture and air movement. And this was quite easily fixed. Slate vents were put in so the warm, moist air could escape through the slate vents. It no longer condensed on the timber, and the problem was solved. So remember air and moisture movement. Now, we're not too far away. We've crashed through lofts. We'll now plummet through floors. If you have a suspended timber floor, as you can see here, and you can get underneath it into what is rather optimistically, in some cases, called the crawl space, then you can, in theory, insulate from below. That's what happened here. This is sheep's wool, again, getting pinned in between floor joists. So you can insulate from underneath if you can get underneath the floor. Oh, what's happened there? But in many cases, if you are insulating a suspended timber floor, it will be a case of lifting up floorboards, putting in timber runners down at the bottom of the joists, and putting in a board-based insulation onto those runners. The picture that you can see here, that's hemp fibre board. Wood fibre board would work as well. So the floorboards were lifted up, the insulation was put down, U-value improvement 2.4 down to 0.7, which is pretty good. And here we can see the floorboards being reinstated. In a more recent project, we got a bit smarter, and rather than lifting up all the floorboards, we lifted up a few here and a few there, and we fed the timber runners through, we put the insulation through, and then we reinstated the boards that we'd lifted up. So this is a relatively straightforward way of insulating a suspended timber floor. If you have a solid floor, however, that is much harder to make thermal improvements to. You can dig out solid concrete floors. That's what we did here. I say we, I didn't do any of the digging. This lad did the digging. But we dug out a solid concrete floor. We put down a big layer of lightweight expanded clay aggregate, as it's termed, LECA for short. So we put that down, and we then put a lime concrete floor on the top. Now that makes a very substantial thermal improvement, but it is time consuming, it is messy, and it's not really something that you could do in a building which you were living in. So you might do this as part of a big refurbishment, but you would almost certainly need to move out while it was happening. You certainly wouldn't be able to use the room because it takes about 6 weeks for the lime concrete to fully cure. This was another project that we did. This one was up in the Highlands, where we dug out a solid floor and we were putting down a lime concrete floor, and we incorporated underfloor heating, which was connected to a ground source heat pump. We don't do that much work on renewables, and we tend to stick mostly to just fabric improvements, but in this case the opportunity to test this out was there, and it was in the end pretty successful. So that's a lime concrete floor getting laid on top of this underfloor heating. Now, we did think, well, if we've got a solid concrete floor, rather than digging it out with all the cost and the mess and the nuisance value of that, couldn't we put something down on top? And we did. We put down some aerogel board. Excellent thermal improvement, 3.9 to 0.8. So we were just off to celebrate. But then we realized we couldn't go and celebrate because we could no longer open the door, because we had raised the floor level by 50 mil and the door would no longer open. So we had to get the saw, which you can see just poking out there, and saw the bottom off the door. We then had to make a little ramp so that people could get in and out the room. And it was just a little bit more complicated than we first thought. But it sure was easier than digging the thing out. Lesson there is, yes, we can improve solid floors, but it's much easier to improve suspended timber floors. Right, last couple of slides now. I've got no idea if I've stuck to time or not. Again, if we were live, I could see people start to nod off, look out the window, take out their phones, that sort of thing. So I'll just assume that everybody's still listening and engaged. Very quick slide about energy performance certificates. We've just done a case study looking at refurbishing a building in Edinburgh. And as part of that, we did various bits of work around energy performance certificates, because it's going to be a very important part of how buildings are dealt with. I mean, it already is, but it's going to become more important going forward. So what did we find? Well, we found, first of all, that in some ways you get what you pay for when it comes to energy performance certificate assessments. That shouldn't be the case. They should all be standard. But if a surveyor is paid to take their time and do a very thorough assessment, measuring the building properly, measuring all the bits of a room in the roof, for example, that can affect the outcome of the EPC. So it's worth getting the assessor to do proper measurements, to take their time over things and record things thoroughly. Another lesson which we learned was that if the assessor can't see a measure, then you as the building owner have to show evidence for it. So if you get 100 mil of insulation put in your room in the roof and you finish it nicely with plasterboard, and the EPC assessor comes along, you need to have evidence to show that that work has been done. So that's certainly a lesson that we learned there. In terms of the final outcome, we managed to get the building up to a band D. We are going to get it up to a band C at some point in the next month or so by making a few short, small changes. And we could get it to a B if we put some renewables in. So what all of this work showed was that, yes, you can achieve a good EPC banding for traditional buildings, but you need to be careful about evidencing work which has been done, and you need a proper survey to be carried out. Right, there we go. That's all I'll say for now. Just to finish up, there's an absolute wealth of information which underpins what I've been talking about today. There's a short guide to fabric improvements, which is essentially today's presentation, but written out and a few other things added in. So that's a good place to start. There's lots of case studies, which are site-based bits of work which we've carried out. There's technical papers, so if you really want to get in about the nuts and bolts of it, you can look at those. That's my email address. I'm very happy for people to get in touch with me about their buildings or things that they might want to do or ask about. If you are emailing me, then send pictures. Otherwise, my first reply will be, thank you for inquiry. Please send pictures. So there's something that'll save you at least one extra email. So that's all I'll say for now. Happy for people to ask questions now, or email me, or look at the literature. Yeah, that's all.